United States Air Force has been trying to retire this aircraft since the 1960s. Satellites were supposed to replace it, then the SR-71 took over in the late 1960s, then drones arrived in the 2000s, and then stealth fighters were supposed to make it obsolete. None of them lasted. In 2026, the Pentagon is keeping the U-2 Dragon Lady alive for reasons that have nothing to do with nostalgia. They're giving it new electronic warfare upgrades, an artificial intelligence co-pilot, and a job so sensitive that no satellite on Earth can do it. The U-2 first flew in July 1955. Kelly Johnson designed it at Lockheed's Skunk Works, and only 104 were ever built. Roughly 30 remain in Air Force service today. The current fleet averages nearly 40 years old, and the youngest airframe rolled off the production line in 1989. And yet in 2026, this is the aircraft combatant commanders from Cyprus to Korea keep demanding for their most sensitive missions. The retirement history of the Dragon Lady reads like a catalog of failed replacements. Spy satellites were going to make manned high-altitude reconnaissance obsolete in the early 1960s, but they didn't. The SR-71 Blackbird arrived to replace the U-2 in the late 1960s. Yet the Blackbird retired in 1998 while the U-2 kept flying. In the 2000s, the RQ-4 Global Hawk drone was going to take over. And now the Global Hawk is scheduled for its own retirement in 2027. The U-2 is still airborne. The Air Force's official reasons for finally pulling the plug in fiscal year 2026 are real. The cost per flight hour keeps climbing, parts manufacturers have disappeared, and the pilots wear pressurized suits that are basically spacesuits. The training pipeline is so demanding that the Air Force struggles to replace retiring crews, and the airframes themselves average nearly 40 years of hard service. Flying the Dragon Lady isn't like flying any other aircraft. The pilot climbs into the cockpit wearing a full-pressure suit, the same kind of equipment astronauts use, and for missions that stretch past 10 hours, the pilot can't eat normally, can't move freely, and can't leave the seat. The aircraft lands on a single bicycle-style main gear and two outrigger wheels called pogos that drop away after takeoff. A second pilot chases the landing in a high-performance sports car, radioing altitude readings because the U-2 pilot can't see the runway from the cockpit. Fewer than 30 pilots per year complete the training pipeline at Beale Air Force Base, and the physical requirements disqualify most candidates before they ever touch the controls. But operational reality keeps overriding the spreadsheets. The U-2 flew missions over Afghanistan for 2 decades, providing real-time intelligence to troops in contact with enemy forces. It has monitored North Korean missile tests, tracked Russian naval formations in the Black Sea, and surveyed damage after natural disasters. In February 2023, a Chinese surveillance balloon drifted across the continental United States. The Pentagon's response wasn't a satellite pass, it wasn't an F-35 intercept, and it wasn't a drone strike. It was a U-2 Dragon Lady. The Air Force released the cockpit photograph showing a U-2 pilot staring across the gap at the Chinese balloon from above it, collecting intelligence that satellites couldn't provide in real time. The balloon was moving, and the U-2 could move with it. Congress has noticed. Every time the Air Force tries to zero out the U-2 budget, lawmakers push back. The fiscal 2024 budget still included $16.8 million in research and development, $54.7 million in procurement, and $17 million in operations and maintenance for a plane that was supposed to be headed for a museum. The House Armed Services Committee has repeatedly inserted language blocking full retirement until a verified replacement exists, and no such replacement has materialized. The Chinese balloon incident exposed a problem that space-based assets can't solve. Satellites follow predictable orbits, and adversaries know exactly when a spy satellite will pass overhead, so they can hide sensitive activity in the gaps. A satellite can't be retasked in minutes to chase a new target. It can't loiter over one location for hours while shifting its sensors as conditions change. And it can't beam real-time intelligence directly to a squad of soldiers on the ground who need to know what's over the next ridge. The assumption that newer technology always wins would suggest the U-2 should have died decades ago. The opposite is true. The latency problem is worse than most realize. A satellite in low Earth orbit sits roughly 300 to 500 miles above the surface. Radio signals travel fast, But the round-trip delay adds up when multiple ground stations, relay satellites, and processing centers sit between the sensor and the soldier who needs the image. Weather can block optical satellites entirely, and cloud cover over a target area means waiting hours or days for the next clear pass. The U-2 flies below the weather, looks down through thin, high-altitude air, and its pilot can decide in seconds whether to retask the sensor, shift orbit slightly, or call for support. The U-2 solves all of these problems by operating above 70,000 feet. At that altitude, the sky begins to darken. The curvature of the Earth becomes visible, and the horizon stretches for hundreds of miles. Most fighter jets can't reach that high, and many ground-based air defense systems struggle to engage a target that flies above their engagement ceiling. The U-2 can stay there for hours. Its single General Electric F118 turbofan engine sipping fuel while the pilot watches and listens. The modular payload bay is what makes this altitude worth the effort. The U-2 can carry the ASARS-2 synthetic aperture radar in its nose, which can spot vehicle-sized objects through cloud cover and darkness from extreme standoff distances. Or it can mount the SYERS-2C multispectral sensor, which collects imagery across multiple spectral bands, allowing analysts to distinguish between real military equipment and decoys. Or it can fly with the AOSIP Signals Intelligence Suite in underwing pods, listening for radar emissions, radio chatter, and electronic signatures across a wide spectrum. These packages can be swapped between missions in days, not the months required to design and launch a new satellite. When a new threat emerges, the U-2 can be reconfigured to detect it while a satellite is stuck with whatever camera it launched with. There's another factor that satellites and drones can't replicate. The U-2 carries a human pilot who can interpret what the sensors see in real time, make judgment calls about which targets matter most, and communicate directly with commanders on the ground. An algorithm can detect a convoy, but a pilot can notice that the lead vehicle has a particular antenna configuration that signals a command post and redirect the entire sensor package to track it before the opportunity passes. The RQ-4 Global Hawk was supposed to do the same job without a human pilot, but the Global Hawk carries a smaller payload, it operates at lower altitudes, and it's being retired in 2027. The classified RQ-180 may eventually fill the gap, but until that aircraft is publicly acknowledged and operational, the U-2 remains the only platform that combines that altitude, that endurance, and that payload flexibility in a single airframe. Raw altitude and endurance explain why the airframe is still useful, but they don't explain why the Pentagon is writing new checks in 2026. The real story is inside the cockpit, where the U-2 has become a flying laboratory for systems that will eventually control America's next-generation fighters. The hidden advantage is open avionics architecture. Most military aircraft run proprietary software that's locked to specific hardware, so changing a sensor or adding a new radio requires years of integration testing and millions of dollars in contract modifications. The U-2 doesn't work that way. Its avionics were designed with an open backbone that allows engineers to plug in new payloads, test them in flight, and field them in months rather than years. In 2014, engineers added 4 different OMS-compliant payloads to a single U-2 in just 3 weeks. By early 2015, the total had grown to 7 payloads on one airframe. A few years earlier, each of those payloads would have demanded its own dedicated test flight program. In September 2020, a U-2 from Beale Air Force Base made history. It became the first military aircraft to fly with a Kubernetes cluster on board, pooling computing power across 4 flight-certified computers to run machine learning algorithms in real time. Kubernetes is the same container orchestration system that runs cloud servers at Amazon and Google. On the U-2, it meant that mid-flight, engineers could push new code to the aircraft, so the U-2 was updating its own brain while the pilot was at 70,000 feet. This wasn't a ground test. This was a combat-coded airframe, airborne, with new software loading into its mission computers during the mission itself. 3 months later, in December 2020, an artificial intelligence algorithm named R2 assumed control of the U-2 sensors and navigation systems during a live reconnaissance mission from Beale Air Force Base. The human pilot monitored the flight, but for the first time in American military aviation, a machine was co-piloting a combat-coded aircraft. RTU managed the radar, the cameras, and the navigation while the human pilot handled flight safety and communications. The platform chosen for this test wasn't the F-35, and it wasn't a new drone. It was the U-2 because its open architecture could accept the AI integration in weeks instead of the lengthy integration cycles required on closed fighter platforms. In March 2026, BAE Systems announced a new contract to update the U-2's AN/ALQ-221 Advanced Defensive System. The upgrades include software that can detect and counter electronic threats that didn't exist when the system was first designed. The AN/ALQ-221 has been matured over 6 decades, and the 2026 refresh keeps it relevant against modern surface-to-air missile radars and jamming systems. BAE Systems described the U-2's modular design and open avionics architecture as the reason they can develop, test, and field new capabilities quickly. The system includes long-range sensors and onboard processing, giving the pilot situational awareness and self-protection in contested airspace. Behind all of this is the Dragon Star program. That stands for Sensors Technology and Avionics Refresh, and it's making the entire U-2 fleet fully compliant with Open Mission System standards. At the center of the upgrade is the Einstein box, officially called the Enterprise Open Systems Mission Computer version 2.0. This box is the translator between the aircraft's flight-critical systems and any new sensor or radio that complies with open standards. Contractors can build new payloads without proprietary lock-in, so the U-2 becomes a plug-and-play platform, continuously updated instead of replaced. But open architecture on a reconnaissance plane is only half the story. The U-2 is now doing something that no F-22, no F-35, and no drone in the current inventory can match. It's bridging the gap between weapons that were never designed to talk to each other. Open architecture sounds like a procurement detail. On the U-2, it does something no other aircraft in the Air Force can manage. It solves a communication problem that's quietly crippling America's most expensive fighters. The F-22 Raptor uses a data link called IFDL. The F-35 Lightning II uses a different data link called MADL. Both were designed to be stealthy, which means they can't be detected by enemy sensors, but they also can't talk to each other. An F-22 can't share targeting data directly with an F-35, and neither aircraft can connect to the standard Link 16 network that older fighters, ships, and ground troops use. America's 2 most advanced fighters are deaf to each other and to most of the rest of the force. The U-2 can host all 3 of these networks simultaneously, plus the integrated broadcast service. Its open architecture allows it to receive data on one frequency, translate it inside the Einstein box, and retransmit it on another. The Dragon Lady becomes a high-altitude switchboard, connecting networks that use completely different protocols. This isn't a future concept. It has already been demonstrated in combat exercises. In 2015, under Project Iguana, a U-2 passed data between an F-22, 2 F-18s, ground troops using portable rover terminals, and a command center. The F-22's stealth data link fed targeting data to the U-2. The U-2 translated that data into Link 16 format and pushed it to the F-18s and the soldiers on the ground. All participants received the same operational picture, even though the stealth fighters couldn't communicate directly. In 2019, Project Riot went further. An F-35 detected a ballistic missile launch with its onboard sensors and relayed that information through the U-2 to a command center, where a commander made a targeting decision far faster than traditional relay chains allow. The U-2 didn't just carry the message. It translated between 2 stealth fighters that couldn't speak the same language. This is precisely the kind of capability the Advanced Battle Management System and the Pentagon's Joint All-Domain Command and Control Initiative were designed to achieve. Air Force officials have been explicit about where this leads. Colonel Joshua Williams, the Program Executive Officer for Intelligence, Surveillance, and Special Operations Forces, stated in 2023 that the Air Force is using the U-2 as a surrogate platform to decrease risk for 5th-generation fighters. His words were direct. All we're doing is decreasing risk and increasing the technical maturity for stuff we'll use on the F-35, F-22. Colonel William Collins, the senior materiel leader for high-altitude ISR, added that the focus is on code-compliant processors with open mission systems that can be used on 5th-generation and 6th-generation platforms. The U-2 is surviving as the test bed for the networking architecture that is expected to control the F-47 and its collaborative combat aircraft wingmen. That's why the 70-year-old airframe matters for the 2030s. The F-47, America's 6th-generation fighter, is being designed around networked warfare. It's expected to need a node above the battlefield to fuse sensor data from its drone wingmen, from space assets, and from other fighters into a single picture. The U-2 is already testing that architecture at the edge of space, with an open brain that can accept new sensors as fast as engineers can write the code. The Dragon Lady was built to take photographs over the Soviet Union with a film camera, and she's ending her career connecting America's next-generation fighters to the battlefield of the future. The Pentagon keeps scheduling the U-2's funeral, and the Dragon Lady keeps proving it can do jobs that satellites, drones, and even stealth fighters can't match. A 70-year-old airframe with a Kubernetes brain and an AI co-pilot is orbiting at the edge of space, bridging the gap between America's most advanced weapons and the battlefield networks they can't access alone. The Dragon Lady wasn't built for this war, but she's the only one ready for the next one. Join us as we break down the F-47, the 6th-generation fighter that will depend on exactly this kind of networking to dominate the skies. From its inception, the Russian Su-57 stealth fighter caused quite a stir. Its advanced capabilities have raised concerns in other nations, including the United States. As Russia's first 5th-generation stealth aircraft, the Su-57's performance has been compared to the F-22 Raptor, one of the United States' most formidable fighters. But can the Su-57 match or even surpass the capabilities of Western aircraft? In a dogfight, would the Su-57 have the upper hand over the F-22? Or would the American fighter remain dominant? Join us as we explore the insane capabilities of Russia's $273 million stealth jet, which will destroy the West. The Su-57, Russia's advanced 5th-generation stealth fighter, has sparked significant debate since the first day. As the successor to the iconic flanker and a product of over a decade of development, it has drawn mixed reactions. While it represents advanced Russian aviation, some in the West argue it is merely a derivative design. Despite being positioned as the future of the Russian Air Force, only a limited number have been produced, raising questions about its viability. Stealth aircraft became a priority for military powers during the 1980s, with the United States leading the way through the Advanced Tactical Fighter program that ultimately produced the F-22 Raptor. However, misconceptions persist about stealth technology. Contrary to popular belief, stealth does not render an aircraft invisible to radar. Instead, it minimizes detection time, delaying an enemy's ability to achieve a radar lock. This principle underpins the designs of the F-22, an air dominance fighter meant to neutralize threats before adversaries can respond, and the B-2 bomber, built to evade defenses and penetrate deep into enemy territory. With the Su-57, Russia aimed to combine stealth with maneuverability, promising an aircraft capable of countering Western advancements. But is it an underestimated game changer or merely overestimated propaganda? In response to emerging technologies in military aviation, Russia adopted a different approach, prioritizing high performance over stealth. This philosophy led to the launch of their 5th-generation jet program, known as the MFI. The program aimed to develop a competent aircraft with moderate radar cross-section reduction. This effort culminated in the creation of the MiG-1.44, which ultimately failed, showing the broader challenges Russia faced during the 1990s. Despite the MFI program's shortcomings, Sukhoi took the initiative to independently design a next-generation fighter, resulting in the S-37 Berkut. This self-funded project was a technological demonstrator, showcasing advanced capabilities, including its iconic forward-swept wing design. The S-37 symbolized a vision for the future of the Russian Air Force, inspiring further innovation. By the early 2000s, following the MFI's failure, the Russian government launched a new program called the PAK-FA, also known as the Prospective Airborne Complex of Frontline Aviation. Sukhoi and Mikoyan had very different strategies for the PAK-FA competition. Mikoyan suggested a team effort where three design bureaus, Mikoyan, Sukhoi, and Yakovlev, would work together, with the winner leading the project. On the other hand, Sukhoi wanted to lead the entire project from the start, including everything from design to production, working closely with suppliers and research teams. Their aircraft designs also showed different priorities. Mikoyan's prototype was smaller and cheaper, weighing 16 to 17 tons and powered by two Klimov VK-10EM engines with about 10 to 11 tons of thrust each. Sukhoi's T-50 was bigger and more powerful, weighing 22 to 23 tons and using two AL-41F1 engines with 14.5 tons of thrust each. In April 2002, Sukhoi won the competition and became the lead designer for Russia's next-generation fighter. The Ministry of Defense chose Sukhoi for its strong proposal and its proven track record in creating Su-27 variants and successful exports during the 1990s. Flight tests were expected to begin in 2007. However, its production has faced numerous delays, highlighting ongoing challenges in fulfilling this ambitious vision. Russia's fifth-generation fighter jet remained secret for years, sparking intense debates on military forums, blogs, and news outlets. However, the veil was lifted in 2010 when the first images and videos of the Su-57, previously known as the T-50, emerged. The footage showcased the aircraft's maiden flight, captivating the media. Critics quickly dismissed it as an imitation of the F-22 Raptor. But the truth lies somewhere in between. The Su-57 stands out as a unique platform with distinct design choices. While its wing shape may resemble American fifth-generation fighters, the resemblance ends there. Unlike the F-22 or F-35, the Su-57 incorporates design elements from the flanker series, such as engines housed in gondolas and a tunnel structure between them, enhancing lift and maneuverability. The aircraft's canted vertical stabilizers reduce radar visibility, a crucial feature for stealth, and function as control surfaces, a concept reminiscent of the YF-23. This American prototype was lost to the F-22. Interestingly, the Su-57's nose section resembles the YF-23's naval variant concept, the NF-23, more closely than the Raptor. Additionally, the Su-57 integrates horizontal stabilizers and leading-edge root extensions, which act like canards during flight to maximize maneuverability. These design choices highlight its focus on agility and versatility. From its prototype stages onward, the Su-57 has demonstrated a blend of innovation and inspiration, solidifying its position as a distinctive and formidable aircraft. From its inception, the Su-57 has showcased a design philosophy centered on maneuverability and versatility, setting it apart as a unique player in fifth-generation fighter jets. Unlike the advanced stealth coatings of the F-35 and F-22, the Su-57 uses radar-absorbent materials sparingly, focusing on critical areas like hatches or sections prone to radar wave scattering. This limited application reduces the jet's radar cross-section by 20% to 90%, far from the exaggerated claims of massive reductions. While the Su-57 cannot match the stealth of its American counterparts, it's stealthy enough for Russian standards. Modern radars would still struggle to track a target with an RCS below 1 square meter. However, the Su-57's stealth effectiveness is hindered by its exposed engines in the rear, which likely results in a higher RCS compared to the F-35 and F-22. While some media criticize details like exposed screws, these aren't a significant factor, as even the F-35 and F-22 have similar features and maintain exceptional stealth capabilities. The real challenge for the Su-57 lies with its engines. Russia repeated a familiar Cold War mistake by starting the development of the aircraft before designing its intended engines. While other successful jets like the Rafale and Su-27 also began testing with interim engines, they quickly transitioned to their proper power plants. The Su-57, in contrast, still relies on engines not explicitly optimized for its design, limiting its full potential. The story of the Su-57's engine development is long and still unfinished. Currently, the Su-57 jets in production are powered by AL-41F1 engines, which are closely related to those used in the Su-35. While these engines are reliable and robust, they are not the original design and vision for the Su-57. Instead of being based on the AL-41FS developed for the older MFI program, They are adaptations of the older AL-31 engines. This means that unlike some fifth-generation fighters, the Su-57 may not achieve sustained supercruise, flying at supersonic speeds without afterburners when carrying a full combat load. For comparison, even the Su-35 can only achieve supercruise in a lighter configuration. On the bright side, the AL-41F1 engines feature 3D thrust vectoring, giving the Su-57 exceptional agility and maneuverability. The Su-57 is a formidable dogfighter with a thrust-to-weight ratio of over 1, even in combat configurations. However, modern air combat has shifted away from traditional dogfights, making this capability less critical in most scenarios. The future engine for the Su-57, called the U-30, is expected to bring substantial improvements. It's designed to enable supercruise at speeds up to Mach 1.5, incorporate serrated nozzles like the F-35's F-135 engine, and potentially introduce a flatter, stealthier nozzle design inspired by the S-70 Okhotnik drone. These upgrades aim to improve stealth and reduce the visible titanium areas affecting the Su-57's radar signature. However, it's unclear when these new engines will enter service. One of the Su-57's most promising developments is its collaboration with advanced drones like the S-70 Okhotnik. This wingman drone is far more focused on stealth, with a sleek design and large payload capacity. Working alongside the Su-57, these drones could change the dynamics of air combat. For instance, the Su-57 or an AWACS aircraft could identify enemy targets, while the S-70 drones engage them undetected. This teamwork could make the Su-57 and its drones a powerful offensive or defensive force. Russia is developing a new data link system called OZOD, similar to NATO's Link 16, to support this integration. This system would enable seamless communication between manned aircraft and drones, enhancing operational efficiency. The S-70 has undergone several successful test flights and continues to advance through its development phase, promising a significant leap in Russia's air combat capabilities. The Su-57, Russia's advanced fifth-generation fighter jet, is more than just a concept. It's a tangible project with prototypes in limited operational use. However, the ongoing war in Ukraine and the strain on Russia's military resources raise a critical question. Where will the funding come from to support such ambitious and costly projects? Initially, India partnered with Russia in 2007 to co-finance the Su-57's development under the PAC-FA program. In exchange, India would receive a two-seater variant and the rights to produce the aircraft domestically. However, the program faced significant setbacks, including delays caused by engine development challenges and the integration of entirely new avionics, radar systems, and sensors. Frustrated by these delays, India withdrew from the project in 2018. It retained the option to purchase the finished aircraft later, if it ever reached mass production and full operational capability within the Russian Air Force. Russia initially planned to produce 200 Su-57s, but drastically scaled back the goal to a single squadron of 12 aircraft. This number was later adjusted when, in 2017, a contract for 76 units was signed. Despite this, progress has been slow. To date, only around 10 Su-57s are reportedly in operational service. The Su-57 has allegedly been used for testing in Syria and even deployed in the war in Ukraine. Reports suggest it may have engaged in air-to-air combat, with claims of a possible kill against a Ukrainian Su-27. However, these claims remain unverified and fall into the realm of speculation. Funding, production delays, and operational challenges continue to overshadow the Su-57's development, raising doubts about the project's future viability amidst Russia's current economic and military constraints. This conflict has been as much about propaganda as it has been about military advancements, creating the impression that the Su-57 is a game-changing aircraft in combat is a powerful tool for Russia to appeal to potential buyers worldwide. However, it's crucial to approach such claims with caution and a critical mindset. Now, addressing the big question, how would the Su-57 fare against America's finest? The F-22 Raptor or the F-35 Lightning II? Let's delve into its capabilities, focusing on its electronics and weaponry. The Su-57 is equipped with the advanced NO-36 Belka AESA radar system, which consists of 5 distinct antennas. The primary X-band antenna provides long-range detection, and target engagement capabilities. Two additional X-band antennas on the sides enhance coverage, extending to approximately 270 degrees. Furthermore, two L-band antennas integrated into the wings support electronic warfare functions, broadening its defensive capabilities. At the front of the aircraft, there's the infrared search and track system. This system can detect thermal signatures from enemy aircraft and guide infrared missiles without needing the radar. It is similar to the electro-optical targeting system on the F-35. Notably, this is an advantage over the F-22 Raptor, which lacks a comparable IRS system, though future upgrades might address this gap. The Su-57 also incorporates sensor fusion, where its onboard computer integrates data from multiple sensors to improve the pilot's situational awareness. While this is a step forward, it doesn't match the advanced capabilities of the F-35 distributed aperture system and the helmet-mounted display, which offer unparalleled situational awareness and targeting accuracy. One notable drawback of the Su-57 is the absence of an integrated targeting pod, unlike the F-35. The F-35 can engage ground targets using its internal systems while maintaining its stealth profile, a significant advantage in modern combat scenarios. So to conclude the comparison, the Su-57 is a formidable aircraft with features that outpace fourth-generation and even advanced fourth-plus generation fighters. However, in a head-to-head comparison with the F-22 or F-35, it falls short in several key areas, particularly stealth and electronic warfare systems. While impressive in its own right, it remains a step behind its Western counterparts. The Su-57 is undoubtedly a remarkable fighter, but what lies ahead for this program? While the Su-57 isn't flawless, it does showcase strong capabilities. It features advanced radar and avionics, respectable stealth attributes, and powerful engines, though these engines have yet to meet the originally planned specifications. The anticipated Su-57M upgrade is expected to include these improvements, along with advanced systems. However, futuristic elements like autonomous drones remain largely conceptual for now. In combat scenarios, the Su-57 poses a significant challenge. Equipped with R-37M long-range missiles capable of striking targets over 200 kilometers away, it could potentially engage adversaries like the F-22 and F-35 before being detected. Russia envisions the Su-57 as a command aircraft, leading jet teams to enhance battlefield surveillance and support. However, the program faces substantial hurdles. Current production numbers are low, with only 10 to 15 operational Su-57s and an order for 76 more. Even with these, the fleet falls short of matching the U.S. F-22 inventory and the extensive fleet of over 1,000 F-35s deployed by the U.S. and NATO forces. Interestingly, while debates often pit the Su-57 against Western fighters, the Chinese J-20 may represent a more immediate concern for the U.S. With its serial production and growing numbers, the J-20 could more effectively challenge the balance of power than the Su-57. The J-20 stealth fighter is designed to dominate the skies with cutting-edge technology. Its advanced sensors and data systems give the pilot a complete view of the battlefield while using stealth and electronic warfare to keep enemies in the dark. The aircraft has a suite of sensors that provide a 360-degree view, and its nose-mounted systems are tailored for detecting and engaging air threats. Though exact details about its radar remain secret, experts believe the J-20 uses a high-performance AESA radar capable of tracking targets up to 200 kilometers away and engaging multiple enemies simultaneously. It also includes electro-optical targeting systems and infrared sensors, similar to those on the F-35, making it especially effective against stealthy opponents. Pilots enjoy a fully digital setup inside the cockpit with a massive touchscreen display, additional auxiliary screens, and a wide-angle holographic HUD for critical data. The helmet-mounted display lets pilots aim and fire weapons by looking at the target, even at extreme angles. Recent reports suggest the J-20 is also capable of airborne early warning and control, further boosting its versatility. With all these features, the J-20 blends stealth, precision, and cutting-edge avionics into one formidable package. The J-20 fighter jet is designed to carry advanced weapons for various missions. Its primary weapons bay can hold long-range air-to-air missiles like the PL-15 and PL-21, as well as precision-guided bombs such as the LS-6 series. Two smaller side bays near the air intakes are made for short-range missiles like the PL-10. These side bays are built for stealth, letting the doors close quickly before firing, making launches faster and harder to detect. The central bay can fit up to 4 long-range missiles, while the side bays each hold 1 short-range missile. By 2023, reports suggested China was working to boost the J-20's missile capacity. A new staggered setup could allow 6 PL-15 missiles to fit internally, and a slimmer missile called the PL-16, designed with folded fins and a compact frame, is also in development. Despite its smaller size, the PL-16 matches the PL-15 in performance. The J-20's primary mission is air combat, using missiles to take down enemy aircraft and critical aerial targets. It might also handle precision strikes with air-to-ground weapons or anti-radiation missiles. While its wings can carry extra fuel tanks or larger weapons like the PL-17, this would reduce its stealth, so it's not the jet's primary role. Interestingly, the J-20 doesn't have an internal cannon, hinting at its focus on long-range battles rather than close dogfights. Its design prioritizes precision and power when hitting targets from afar. The J-20 stealth fighter is designed with a brilliant mix of features to reduce its radar visibility. Its shape uses canard wings paired with smooth extensions near the leading edges to scatter radar waves effectively. The sleek forebody, radar-friendly canopy, and specialized materials help it achieve stealth like the F-22. Its air inlets, called DSI, are cleverly designed to hide the engine from radar, while also being lightweight and simple. The J-20's weapons bay has flat bottoms, doors have jagged edges, and cooling vents have mesh covers to improve stealth further. While some argue that using canards could hurt its stealth, experts point out that canards can work with low observable designs, as seen in other stealth aircraft. Advanced flight controls and careful engineering make them viable for stealth. The aircraft also uses composite materials and radar-absorbing paint. During peacetime, a special reflector makes it visible to other planes, enhancing safety and reducing training risks. This reflector can be removed in combat. Over time, the J-20 has evolved to include better engines and stealth-enhancing features, especially in its newer models. While its rear stealth isn't as advanced as the F-35, its front-facing stealth is impressive and better than the Su-57. Analysts believe the J-20 can use its stealth to strike targets in cluttered airspaces, showing it's a serious player in modern air combat. In a nutshell, the J-20 is formidable. The future of the Su-57 is uncertain, especially given the pressures on Russia's defense industry due to the ongoing conflict in Ukraine. Nonetheless, its design and the F-22 will likely influence the development of next-generation fighter aircraft for years to come. Despite criticisms, the Su-57 remains an impressive platform, hinting at the potential change of the future of aerial warfare. America's secret ghost jet may soon appear on the USS Gerald Ford, shocking Pentagon officials and rivals. This tailless, triangle-shaped fighter boasts smart skin sensors, laser weapons, and hypersonic speeds of over 6,000 miles per hour. It can even command a swarm of robotic wingmen. Earlier stealth jets seem obsolete in comparison. Has the U.S. Navy just rewritten the rules of aerial warfare? And how will China and Russia react to this invisible predator of the skies? Join us as we unveil the 7th-generation fighter jet before it makes it on the United States aircraft carrier. The sky above the USS Gerald Ford lit up with a bright blue flash as something incredible took place. After nearly a century of struggle, the United States Navy had finally solved one of its biggest challenges. Carrier-based jets could now match or even surpass land-based fighters. For years, aircraft carriers had a major disadvantage. Their jets had to be smaller, lighter, and carry less fuel compared to those launching from land. As countries like China and Russia built powerful land-based fighters and long-range missiles, many experts doubted whether carriers could hold their ground in modern warfare. That changed with the Navy's next-generation air dominance fighter. Unlike the older FA-18 Super Hornets, this new jet brought futuristic technology that had once seemed impossible. It wasn't just a single aircraft, it was the leader of a small team. Each NGAD fighter was paired with autonomous drones, commonly called collaborative combat aircraft. These drones carried extra weapons, sensors, and fuel, following the lead fighter's commands while also making quick decisions on their own. A single pilot could now manage what used to take several people. The USS Gerald Ford's firepower grew even stronger with the addition of the Helios laser weapon system. This powerful 150-kilowatt laser could track and destroy incoming missiles and enemy drones almost instantly. Unlike traditional missiles that could run out, the laser remained operational as long as the ship had power. Most people had no idea how fast this technology was advancing. When an Air Force official revealed in 2020 that a test version of the NGAD fighter had already flown, defense experts were caught off guard. The Navy had been quietly working on this breakthrough for more than 7 years, replacing outdated systems from the 1990s with cutting-edge technology designed for the future. The USS Gerald Ford was designed with cutting-edge advancements in mind. As the Navy's most sophisticated aircraft carrier, it featured electromagnetic catapults that propelled aircraft more swiftly and effectively than traditional steam-powered systems. Its nuclear reactors generated the vast energy required for the Helios laser. The NGAD fighter also looked completely different from older jets. It had no vertical tail fins and featured a sleek triangular design, allowing it to fly in ways that would have made traditional aircraft lose control. Advanced computer systems made thousands of tiny adjustments every second to keep it steady and maneuverable. In training exercises, the results spoke for themselves. Against experienced pilots flying F-35s, the NGAD fighter and its robotic wingmen won nearly every simulated battle. The difference was overwhelming. For countries that had spent billions developing anti-ship missiles to keep United States carriers at a distance, this presented a serious problem. With these new jets, carriers could now operate much closer to enemy territory without fear. For the first time since World War II, carrier-based jets weren't just keeping up with land-based fighters, they were better. This wasn't just an upgrade. As the sun set behind the carrier, the new fighter launched into the night, its silhouette blending into the sky. The aircraft represented a development in naval warfare. What happens when these advanced fighters go beyond the clouds and into the vast darkness of space? Could the next generation of American warplanes be used as spacecraft? Engineers across America are already working on technologies beyond those used on the USS Gerald Ford. While naval aviation advances, the next leap is happening in secret labs. The goal isn't just faster planes, it's aircraft that can move between air and space. These next-generation hypersonic fighters could transform aerial combat. Traveling above Mach 5, more than 6,000 kilometers per hour, they could cross continents in minutes. A fighter this fast could fly from New York to Los Angeles in under 30 minutes, making it nearly impossible to track, let alone stop. Building such an aircraft comes with massive challenges. At extreme speeds, air friction generates heat strong enough to melt standard materials. To solve this, the Air Force and NASA are developing heat-resistant composites that can withstand over 2,000 degrees Celsius without breaking apart. Propulsion is another hurdle. Regular jet engines can't function well at extreme speeds or in the thin upper atmosphere. That's where scramjets come in. Unlike traditional engines, scramjets have no moving parts. They use the aircraft's speed to compress incoming air, generating thrust. Since 2018, the Air Force's Mayhem project has been testing scramjet prototypes, gradually improving their performance. Unlike earlier fighter jets, these advanced aircraft wouldn't just fly high, they could briefly leave Earth's atmosphere. By reaching altitudes above 100 kilometers, they could enter a suborbital path, skipping across the upper atmosphere like a stone across water. This would allow them to strike targets with almost no warning, conduct surveillance from altitudes beyond the reach of anti-aircraft weapons, and even deploy small satellites to restore communications in combat zones. The United States military has been quietly funding this research for years. DARPA has been working on airspace transition vehicles since 2020, focusing on designs that can move between the atmosphere and space without rockets or launch pads. But breaking into space creates new risks. Outside Earth's atmosphere, cosmic radiation can damage electronics and pose health risks to pilots. Engineers are developing shielding and radiation-resistant computer systems to keep these aircraft safe. Fuel is another challenge. Traditional jets can refuel mid-air, but space-capable aircraft need an energy source powerful enough to push them beyond most of Earth's gravity and still bring them back safely. Advanced hydrogen propulsion is one possible solution, providing high energy output with only water as a byproduct. The race to develop this technology is already underway. China is rapidly increasing its hypersonic research budget, while Russia's PAKDP program is working on similar aircraft. Any country that masters space-capable fighters will gain a major military advantage. This also raises legal questions. The 1967 Outer Space Treaty bans nuclear weapons in space, but doesn't address conventional weapons or temporary military operations beyond Earth's atmosphere. This loophole has sparked new debates at the United Nations about the future of space warfare. Even the best pilots would need entirely new training for these aircraft. At hypersonic speeds, decisions must be made in milliseconds, too fast for human reaction times. AI assistance and augmented reality systems would have to predict and respond to problems before they happen. The Air Force is already preparing for this future. Specialized bases are being upgraded to support these hybrid airspace vehicles, with reinforced hangars, advanced cooling systems, and specialized fuel storage facilities built to handle the extreme demands of hypersonic flight. While sixth-generation fighters represent the future of modern warfare, these seventh-generation space fighters are something entirely different. The line between science fiction and military reality is disappearing fast. What once seemed impossible is now just a matter of time. As these jets push the limits of technology, the big question is, who or what will be in the pilot's seat? Behind closed doors in high-tech labs across America, engineers have been building the brains of future warplanes long before a single piece of metal is cut. Before these next-generation fighters take shape, their artificial intelligence is already training in virtual battles against the world's best pilots. AI is no longer just a co-pilot, it is being designed to take over entirely. What began as basic autopilot and warning systems soon expanded to flight guidance and real-time threat analysis. Now, cutting-edge AI can autonomously execute complex combat missions, making split-second decisions faster than any human pilot. A breakthrough came with the Pentagon's Project Maven. Launched in 2017, it began by teaching AI to recognize objects in drone footage. Over time, the system evolved to track multiple moving targets, even through clouds, smoke, and electronic interference. The next generation of warplanes will look unlike anything seen before. There will be no cockpits or instrument panels, just advanced processors, cooling systems, and AI-powered decision-making packed inside a sleek, high-speed airframe. These aircraft will be more like flying supercomputers than traditional jets, controlling weapons, sensors, and engines with machine intelligence. The way these planes are built is also changing. In factories across Nevada and California, massive 3D metal printers are already shaping experimental aircraft parts. These machines create complex designs layer by layer, using titanium and carbon fiber, making structures that were previously impossible with older manufacturing methods. This advancement accelerates production at an unprecedented rate. In the past, developing and testing a new design could take several years, involving extensive prototyping, manual adjustments, and countless trial and error phases. Now, with advanced automation and AI-driven simulations, the entire process can be streamlined, reducing development time to just weeks. Engineers can rapidly iterate designs, test performance in virtual environments, and refine prototypes with real-time data, allowing for faster innovation and deployment. Engineers feed designs into simulations where AI runs countless virtual test flights, refining the aircraft before a real one is built. Only the best designs move forward, ensuring each new fighter is an improvement over the last. Military planners see an opportunity in this rapid development cycle. Instead of producing hundreds of identical jets that risk becoming outdated, they can create smaller batches that evolve over time. Each generation learns from the last, making the fleet smarter and more adaptable. Another breakthrough is the concept of smart skin. Instead of mounting separate radar and sensors, the entire surface of these aircraft will be covered in tiny sensors, turning the whole plane into a flying surveillance system. Traditional jets have blind spots, these will have none, detecting threats from all directions and instantly sharing that data with other AI-powered aircraft. This real-time connection gives AI-controlled jets a major edge. Multiple fighters can operate as a single intelligent unit, responding to threats as a team. Smaller, unmanned drone fighters, built at a fraction of the cost, can fly alongside, carrying extra weapons, scouting ahead, or even sacrificing themselves to protect the primary aircraft. But with AI-driven warfare, ethical concerns grow. Military rules state that a human must have meaningful control over combat decisions. Yet at hypersonic speeds, human reaction time simply cannot match AI decision-making measured in microseconds. The Navy has formed an advisory board to address these concerns, ensuring AI follows rules of engagement and minimizes unnecessary harm. However, programming a machine to understand restraint and proportionality remains an unsolved challenge. Technical hurdles also remain. AI-driven aircraft require immense computing power, generating extreme heat. Scientists are exploring quantum computing and advanced cooling systems to keep these machines running efficiently. And while AI has mastered strategy games like chess, aerial combat is far more unpredictable. Training AI pilots in massive simulation environments is key to sharpening their combat skills. The combination of rapid manufacturing and AI autonomy is reshaping aerial warfare. The nation that perfects this technology first will gain an overwhelming advantage, one where warplanes don't just fly, but learn, adapt, and improve with every mission. Even the most advanced fighter jet loses its edge if the enemy spots it from miles away. But what if these new warplanes could completely disappear even from human sight? The most surprising thing about the next generation of fighter jets isn't what they have, it's what they don't. The familiar vertical tails that have defined military aircraft for over a century are gone. Sharp edges and visible engine intakes are missing too. Instead, these jets have a smooth, flowing shape that looks strange to experienced pilots. With soft edges and no clear front or back from certain angles, the design defies traditional aerodynamics and stability rules. It resembles a flying triangle more than a conventional aircraft. This groundbreaking transformation is the result of decades of advancements in stealth technology. The first-generation stealth aircraft, such as the F-117 Nighthawk, relied on angular surfaces to scatter radar signals. The B-2 Spirit bomber improved upon this by incorporating smooth curved contours to further reduce detectability. Today, the most advanced designs push the boundaries even further, striving for near-total invisibility to enemy radar systems. Older planes needed vertical tails for stability, but those tails made them easy radar targets. Engineers replaced them with an advanced flow control system originally tested on the B-2. Instead of stabilizers, hundreds of tiny air jets adjust the aircraft's balance in real time. A computer makes constant corrections, ensuring smooth flight without traditional control surfaces. The aircraft's skin also enhances stealth. Radar-absorbing materials are built directly into the structure, making them more durable than older coatings that wore off. Some sections even contain carbon nanotube layers that absorb radar signals and release the energy as harmless heat. Heat detection is another challenge. Fighter jet engines produce extreme heat, making them easy targets for infrared sensors. New designs cool the exhaust before it leaves the aircraft, then spread the remaining heat over a wider area, reducing their infrared signature. This makes it harder for heat-seeking missiles to lock on. Beyond stealth, these jets are built for adaptability. Older fighters were rigidly designed, meaning upgrading one system often required redesigning the entire aircraft. The new generation features modular components, allowing engineers to swap out weapons, sensors, and avionics quickly without major overhauls. This approach cuts costs and extends the aircraft's lifespan. Instead of waiting years for a completely new model, militaries can upgrade existing jets in weeks. Experts estimate this could reduce costs by 30 to 40% compared to today's most advanced fighters. For radar operators, detecting these aircraft is becoming nearly impossible. Older stealth jets had radar signatures the size of a small bird. Today's fighters appear smaller than a marble. The goal is to become virtually invisible to radar altogether. Even spotting these jets with the naked eye is difficult. Adaptive camouflage panels on their surface can change color to blend with the sky or terrain below. While not true invisibility, this makes them extremely hard to track visually, especially from a distance. Every aspect of these jets is built for real-world combat. Critical areas are reinforced to withstand damage, Maintenance access points are easier to reach, and vital systems have built-in backups. These improvements come directly from lessons learned in modern warfare. Stealth technology has always been a cat-and-mouse game. As enemy sensors evolve, stealth aircraft must adapt. With flexible designs and cutting-edge technology, these new jets are built to stay ahead, ensuring dominance in future battles. As America leads in stealth tech, others race to catch up. How did a marketing move spark a trillion-dollar power struggle? The idea of fighter jet generations didn't start with military strategists or aviation pioneers. It was a marketing move by Lockheed Martin. In the early 2000s, the company needed a way to make its new F-35 fighter stand out. The solution they came up with was to call it fifth generation, making everything else seem outdated. The term caught on. Soon, military officials, journalists, and analysts worldwide adopted the classification. Older jets were retroactively sorted into generations. The Korean War-era F-86 Sabre became first generation, the Vietnam-era F-4 Phantom was third generation, and Europe's Eurofighter Typhoon landed in the fourth generation category. What began as a sales tactic reshaped global defense strategy. Countries now felt pressured to keep up. When China unveiled its J-20 in 2011, state media repeatedly emphasized one point. It was China's first fifth-generation fighter. The message was clear. China had joined an exclusive club previously limited to the United States and Russia. India accelerated its fifth-generation program. Japan prioritized acquiring such capabilities. South Korea launched an ambitious effort to build its own next-generation fighter instead of buying from abroad. This marketing-driven shift overlooked an important fact. Before generational labels took hold, countries evaluated fighters by their capabilities, not arbitrary classifications. The French Rafale and Swedish Gripen featured advanced technologies that rivaled early fifth-generation jets. Yet they were dismissed as merely 4.5 generation. The United States officially moved towards sixth-generation fighters in 2014 with DARPA's Air Dominance Initiative, securing nearly $1 billion in early funding. By 2020, the Air Force confirmed that a demonstrator had already flown successfully, pushing rivals to accelerate their programs. China responded by reorganizing its aerospace sector, pouring funds into AI and advanced materials research. Satellite images soon revealed remote test sites where experimental aircraft could fly unobserved. Despite economic struggles, Russia pressed forward with its PAKDP program to replace the aging MiG-31. Officials highlighted its planned ability to operate at extreme altitudes, an apparent counter to United States' interest in space-capable fighters. European nations, unable to match these investments alone, formed cooperative ventures. The UK-led Tempest project partnered with Italy and Sweden, while France, Germany, and Spain joined forces on the Future Combat Air System. Both programs aim to maintain European defense independence rather than rely on American jets. Historically, new fighter generations emerge every 10 to 15 years. Now, the leap from fifth to sixth generation may take 25 to 30 years due to rising costs and complexity. Seventh-generation concepts might not enter service until the 2070s, marking the longest development cycle in fighter history. Meanwhile, the B-52 bomber offers a different approach. First deployed in 1955, it has been continuously upgraded and could serve for a century, proving that evolution sometimes beats revolution. Lockheed Martin, which started this generational race, continues teasing the future. At its Skunk Works 80th anniversary, a mystery aircraft appeared alongside historic designs like the U-2 and SR-71, potentially America's next fighter. With future programs expected to cost hundreds of billions, international collaboration is now essential. What began as a marketing ploy has reshaped global military aviation, making generational labels a defining factor in national security and defense spending. Can the United States F-35 withstand the threat of Chinese hypersonic weapons? Recent advancements in China's hypersonic technology have raised global concerns, sparking questions about whether the United States is losing its technological edge. Does the U.S. have the capability to counter these hypersonic threats, or is it at risk of falling behind in this critical area of defense? Join us as we delve into the groundbreaking comparison of two ultimate weapons, The F-35 versus Chinese hypersonic threats. China is making fast progress in hypersonic missile technology, putting it at the forefront globally and raising concerns in the United States. One major example of their advancements is the DF-17 missile, which is designed for speed and precision. It is a medium-range ballistic missile that uses solid fuel and is road mobile, meaning it can be transported and launched from various locations. They have also made breakthroughs in thermal protection and cooling systems, which are crucial for managing the intense heat these missiles generate during flight. These developments give China a clear technological advantage, showing their growing strength in modern military innovation. It's certain that they are not stopping anytime soon, because they recently achieved another major breakthrough in hypersonic missile technology, particularly with its thermal protection system. Chinese scientists have made significant improvements by adding steel nose cones to their new missiles. This advancement is crucial because it enhances the missile's ability to survive the extreme conditions it faces during flight. In August, China also announced the development of an innovative cooling device designed to manage the intense heat generated during hypersonic flight. Hypersonic missiles travel at incredibly high speeds, which results in a huge buildup of heat. Without proper cooling, this heat could damage the missile's guidance system, affecting its accuracy and performance. With the new cooling technology, the missile is better equipped to withstand these extreme temperatures, making it less likely to malfunction. This improvement allows the missile to fly more effectively and remain undetected, increasing its chances of successfully reaching and eliminating its target. These technological advances are a significant step forward for China's hypersonic missile program, giving it a performance edge in the field of modern warfare. As the race for advanced weaponry intensifies, these innovations could change the future of missile technology and warfare. One member of Congress is raising concerns. Representative Doug Lamborn, who is part of the House Armed Services Committee, held a hearing for his subcommittee this spring. The mood was serious. One expert on the panel said the United States is clearly falling behind China. Jeffrey McCormick, an intelligence analyst with the Defense Intelligence Agency, stated that China now has the world's leading hypersonic arsenal. The United States still has reason for optimism. Surprisingly, one of the best American hypersonic missiles is being developed by the U.S. Army. Known as the Long-Range Hypersonic Weapon, or by its nickname, the Dark Eagle, this missile has impressive capabilities. It can travel at speeds exceeding 3,008 human miles per hour and has a range of 1,722. The Dark Eagle uses a road-mobile launcher, a feature also preferred by China for its missiles, making it a highly versatile weapon. According to the Army, the missile can fly to the top of the Earth's atmosphere and stay just out of reach of air and missile defense systems until it's ready to strike. By the time it's within range, it's already too late to react. Despite China's advancements, all is not lost for the U.S. The race to develop hypersonic missiles is critical, as China has made remarkable progress in this area. Their scientists have been steadily advancing hypersonic technology and already have fast, maneuverable missiles deployed. China's military continues to look for ways to improve these weapons, and its rapid progress is something the U.S. must be prepared to match. However, the United States is not far behind, and with the right focus and commitment, it can catch up to China. The issue lies in the way the U.S. military approaches hypersonic development. While China has been able to make steady, incremental advances in their missile technology, the United States has focused on separate programs across various branches of the military. This lack of coordination could slow progress. In contrast, China's approach is more streamlined, allowing them to make faster improvements and field more advanced systems. There's still a chance for the U.S. to regain its lead, but it will require strong, focused efforts. We have yet to experience a Sputnik moment where China might test a hypersonic missile in a high-profile launch that demonstrates its serious intentions to use these weapons for strategic purposes. A launch over Guam, for example, could be a powerful signal to the world of China's capabilities and intentions. Until such a moment happens, policymakers like Representative Doug Lamborn, who is raising concerns about the state of U.S. military technology, are crucial. They are pushing for the U.S. to stay focused on developing advanced hypersonic systems to counter China's growing missile capabilities. While there have been some obstacles and challenges in the development of American hypersonic weapons, the U.S. defense industry is known for its strength. With continued investment, collaboration, and focus, it's likely that the United States will catch up to China in this critical area of military technology. The arms race is far from over, and with the right strategy, the U.S. could still emerge as the leader in hypersonic missile technology. This leads us to one important question. Can the F-35 withstand the lethality of the Chinese hypersonic threat? Let's analyze the strength of this American airfighter. The F-35 Joint Strike Fighter is one of the most recognizable fighter jets in the world. Since it began service, this American-made fifth-generation aircraft has flown over 777,000 hours. Currently, 20 nations use the F-35, making it a vital tool for the U.S. and its allies. For years, the U.S. held air superiority with the introduction of the F-22 Raptor. However, both China and Russia now have their own fifth-generation jets and are working on sixth-generation designs. For now, the F-22 and F-35 remain America's top fighters. The F-35 mission systems are like the brain and eyes of the jet, making it one of the smartest aircraft ever built. Packed with advanced sensors and software, these systems give pilots a complete picture of their surroundings, making the jet a powerful tool in modern warfare. Key components include the APG-81 radar, which can track multiple targets over 150 kilometers away, and the Barracuda electronic warfare system, which can detect, jam, and protect against enemy radars. The jet also features a cutting-edge distributed aperture system with 6 infrared cameras that provide a full to 60-degree view, even at night. All this information is fused into a single clear display for the pilot, giving them unmatched situational awareness. Future upgrades include improved sensors, a more powerful radar, and even the ability to control drones during missions. With these advancements, the F-35 isn't just a fighter jet, it's a flying command center built for the future of air combat. Stealth is one of the F-35's most impressive features, making it hard for enemies to detect. Its unique design includes smooth, curved surfaces, precisely aligned edges, and radar-absorbing materials to minimize radar detection. Even the engine is cleverly hidden from view. The jet's advanced air intake system, called the diverterless supersonic inlet, further reduces its radar signature by eliminating gaps that could reflect signals. Remarkably, the F-35 radio cross-section is so small that it's been compared to the size of a metal golf ball from certain angles, even outperforming the stealthy F-22 in some scenarios. Its outer skin, made from durable radar-absorbent material, is designed to last longer and require less maintenance than older stealth aircraft like the F-22. The F-35 also reduces its infrared and visual signatures, making it harder to spot by heat or sight. It carefully manages its radio signals to avoid detection. While low-frequency radars can sometimes detect stealth aircraft, they are bulky, imprecise, and easy to locate, giving the F-35 a significant advantage. For training purposes, it can even use special reflectors to temporarily increase its radar signature. Its cockpit is like something out of a sci-fi movie, designed to give pilots maximum awareness and control. At its heart is a massive 20 by 8-inch touchscreen display, which shows everything from flight data to weapon systems and alerts. Pilots can customize the layout to fit their needs, making it incredibly user-friendly. Beneath this display is a smaller backup screen for emergencies, while advanced voice recognition technology allows hands-free commands. Unlike older jets with head-up displays on the dashboard, the F-35 uses a state-of-the-art helmet-mounted display system. This helmet projects flight and combat information directly onto the pilot's visor, so they can see critical data no matter where they're looking. It even integrates infrared and night vision, allowing pilots to see through the plane for incredible situational awareness. The helmet is so advanced that pilots can lock onto targets and fire missiles without pointing the aircraft directly at them. Each helmet costs a whopping $400,000, but its capabilities are game-changing. While the HMDS had some growing pains, like issues with vibration and night vision early on, it's now more reliable than ever. The latest version boasts improved cameras, sharper displays, and advanced alignment features. The F-35 cockpit and helmet work together to give pilots an unmatched edge in the skies, blending cutting-edge technology with pilot-friendly design. Without going on and on about the capabilities of the F-35, to answer the question, it is unlikely for this American aircraft to be able to directly withstand a hit from a modern Chinese hypersonic missile due to their extreme speed, maneuverability, and difficulty in detection, making them very hard to intercept with current technology. What is the United States Air Force doing concerning the threat that these Chinese hypersonic air force pose? The United States Department of Defense is ramping up spending on hypersonic weapons after years of warnings that China is pulling ahead in this technology. However, this new arms race comes with risks, especially as relations between the US and China continue to worsen. And there's limited information about China's advancements in this field. Hypersonic weapons, which travel faster than Mach 5, aren't a new concept. The US has been testing them since the 1950s. But investment in these systems slowed over the years. Meanwhile, China and Russia have made significant progress in their hypersonic programs. Russia recently demonstrated its capability by using 6 hypersonic Kinzhal missiles in Ukraine, the largest single deployment of these weapons during the war. Other nations, including Australia, South and North Korea, Japan, India, and Germany, are also developing hypersonic weapons. The US is now increasing funding and efforts to catch up, but the timing is tense, with US-China relations at their lowest point in decades. This competition could shape the future of global military power. The US Department of Defense reportedly plans to allocate $15 billion for hypersonic weapons development for the Army and Air Force between 2023 and 2027, as highlighted in a Congressional Budget Office report. This figure excludes the Navy's program, which recently awarded a $1.1 billion contract to Lockheed Martin for integrating hypersonic systems into Zumwalt-class destroyers. Experts have indicated that the US may be lagging behind China in this field. Reports noted that China's 2021 test of a nuclear-capable hypersonic weapon surprised many in the defense sector, showcasing advanced capabilities that exceeded expectations. It has been suggested that America's previous technological dominance, once considered untouchable, is now being challenged by China's progress. Observers have pointed out that this shift has spurred the US to accelerate its efforts in several areas. Concerns have also been raised about the absence of treaties governing hypersonic weapons, a situation some believe could lead to global instability, as seen during the Cuban Missile Crisis. However, analysts have noted that the major powers in this domain appear unwilling to pursue such agreements at present. Despite challenges, US defense officials, lawmakers, and weapons manufacturers continue to advocate for hypersonic technology, with the government now committing significant funding to advance the project. Hypersonic weapons are undeniably expensive, but they offer unique advantages that justify the investment. The US military began exploring hypersonic systems as far back as the 1960s, initially focusing on hypersonic flight for transporting people rather than weapons. By the 1980s, however, the focus shifted. During this period, the Air Force tested the maneuvering reentry vehicles, demonstrating that missiles traveling at speeds of Mach 5 or faster could be guided precisely to their targets as they re-entered Earth's atmosphere. The early 2000s marked a turning point when the US began serious efforts to develop hypersonic weapons under its conventional prompt global strike program. Today, 2 primary types of hypersonic weapons are being developed: glide vehicles and air-breathing missiles. Glide vehicles are launched on rockets and glide through the atmosphere at high speeds, while air-breathing missiles use engines to sustain their hypersonic speeds. Although US hypersonic systems are designed to carry conventional payloads, other nations, such as China, are pursuing nuclear-capable hypersonic weapons. This was evident during China's groundbreaking 2021 tests, which demonstrated the ability to combine nuclear warheads with hypersonic speeds, raising concerns about the global arms race. As the US pushes forward, these advanced systems promise unparalleled speed, precision, and flexibility in modern warfare, making them a critical focus for defense strategies. China has long sought ways to counter US missile defense systems, viewing them as a threat to its nuclear deterrence, according to Lyle Morris, a senior fellow at the Asia Society Policy Institute. Since the early 2000s, China has significantly boosted its hypersonic weapons program, especially after the US withdrew from the anti-ballistic missile treaty with the Soviet Union. With no restrictions on developing anti-ballistic systems, China felt compelled to develop a different kind of deterrent. One key focus of China's efforts has been glide-type hypersonic weapons. These systems start their journey atop a ballistic missile, explains Timothy Heath, a defense researcher at the RAND Corporation. Once the missile reaches a certain altitude, The hypersonic glider detaches and travels at incredible speeds within the atmosphere. Unlike traditional ballistic missiles that follow a fixed trajectory, the glider can maneuver in flight, using the momentum from its launch to strike its target with precision. China claims its hypersonic weapons are ready for deployment, which Heath notes is a step or two ahead of the U.S., whose hypersonic program is still in the testing phase. This progress isn't surprising given China's advanced ballistic missile program and the U.S.'s relative underinvestment in similar technologies over the years. The real game changer with hypersonic weapons isn't just their speed, but their ability to maneuver and evade missile defense systems like the Patriot. These systems, widely used in the U.S. and 17 other countries, struggle to track and intercept hypersonic weapons due to their unpredictable flight paths and the ability to skim the edge of the Earth's atmosphere before re-entering. According to defense experts, hypersonic weapons could potentially outmatch even the most advanced air and missile defense systems in the near future, making them a significant development in modern military technology. With China's successful hypersonic missile tests and rising tensions between Beijing and Washington, it's understandable to worry about the rapid pace of weapons development and heated rhetoric. However, there are significant obstacles to the widespread use of hypersonic weapons in combat. The high cost, around $15 million to $18 million per missile, combined with the practical realities of warfare, where basic weapons like artillery are often more effective, makes their use in battle questionable. Experts like Lau Morris and Timothy Heath are skeptical about hypersonics' actual usefulness on the battlefield. A report from the Congressional Research Service points out that critics believe these weapons don't have clear mission roles, don't significantly improve U.S. military capabilities, and aren't necessary for deterrence. In addition, there's concern that China might share its hypersonic technology with other U.S. adversaries, such as North Korea, Iran, and Russia, all of which are developing their own hypersonic programs. As China and Russia strengthen their defense and technological ties, sharing knowledge on hypersonics wouldn't be surprising, says Elsa Kania, an expert on national security. One of the main concerns about China's hypersonic program is that the U.S. might be caught off guard. The fear of appearing less dominant in defense was especially strong after China's successful missile tests in 2021. General Mark Milley, chairman of the Joint Chiefs of Staff, called these tests China's Sputnik moment, drawing a comparison to the Soviet Union's 1957 launch of the first artificial satellite, which shocked the U.S. Despite the concerns, Heath argues that hypersonic weapons would not be the deciding factor in a conflict between the U.S. and China or any other nation with hypersonic capabilities. The U.S. has a significant edge in other military technologies like stealth aircraft, long-range bombers, aircraft carriers, and submarines, conventional forces that allow the U.S. to project power and dominate adversaries without relying on long-range missiles. As the U.S. continues to invest in hypersonics and other nations develop their own capabilities, it's crucial to establish some sort of agreement on how these weapons should be used in combat. Unfortunately, Morris notes, this may not happen until a major escalation forces both sides to confront the issue. With the current lack of communication between China and the U.S. military, the risk of misunderstandings or miscalculations is high. Furthermore, most significant weapons agreements have historically been between the U.S. and Russia. With Russia pulling out of the New START treaty, the last major nuclear arms control agreement, the hope for any future defense technology agreement seems distant at best. Russia's seventh-generation fighter jet is reshaping the future of air combat. Packed with next-level technology, it is drawing concern from military powers around the globe. With stealth capabilities, advanced weaponry, and unmatched agility, the jet is changing the rules of engagement, forcing nations to rethink their defense strategies and preparedness for the battles of tomorrow. How does this cutting-edge aircraft threaten global air dominance? And what does its rise mean for the future of warfare? Join us as we explore the technology behind the game-changing jet and its potential to disrupt the balance of power in the world. The Su-57 is Russia's newest fighter jet. Built by Sukhoi, it has 2 engines and special features that make it hard to detect on radar. The Russian military started working on this plane in 1999 when they needed something more practical than their earlier design. While Sukhoi calls it the T-50 internally, it's better known as the Su-57. It is a big step forward for Russia, as it is their first military plane built to avoid detection, and they plan to use its design as a blueprint for more stealth aircraft in the future. The Su-57 can do many jobs in one plane. It can fight other aircraft in the air, hit targets on the ground, and attack ships at sea. The plane is hard to spot on radar, can turn quickly in tight spaces, and flies fast without using extra fuel. Its computers all work together, and it can carry lots of weapons. The first test plane took to the sky in 2010. However, getting the design right proved challenging. The team ran into problems with how the plane was built and how its systems worked during testing. Things got worse when the very first plane meant for actual military use crashed before it could even be handed over. In 1979, the Soviets knew they needed better fighter jets ready to fly by the 1990s. They picked Mikoyan to handle this project, and the company started working on the MiG 1.44. Sukhoi was not chosen for this project, but they did not let that stop them. In 1983, they began their research to create cutting-edge fighter technology. This work led to their test plane, the S-32, which they later called the S-37 and finally the Su-47. What made this plane special was how its wings pointed forward instead of backward. When the Soviet Union fell apart, money dried up. This meant the MiG 1.44 project kept getting pushed back. The plane didn't take its first flight until the year 2000, 9 years later than planned. The costs were just too high, so they had to cancel both the MFI and LFI projects. Despite the setbacks, Russia still wanted new fighter jets, and in 1999, the Russian Ministry of Defense started fresh with something called the PAKFA or I-21 program. Because they were struggling with money, they had to be smart about their next fighter jet. Instead of making two different planes to replace the Su-27 and MiG-29, they decided to build one plane that could do both jobs. To keep costs down, they planned to make it smaller than their previous test jets. The new plane would be bigger than a MiG-29, but smaller than a Su-27. It would also be much lighter. The old MiG test plane weighed 28.6 tons, 63,000 pounds, and the Su-47 weighed 26.8 tons, 59,000 pounds. The new design would weigh a lot less than either of those. Sukhoi and Mikoyan had very different ideas about how to handle this big fighter jet project. Mikoyan wanted all three design teams, themselves, Sukhoi, and Yakovlev, to work together as partners. The team with the best design would take the lead. But Sukhoi came with their plan. They wanted to be in charge from day one. They had already figured out who would build the engines, who would make the electronics, and which research labs would help out. Their proposal covered the whole process from start to finish. The two companies also had different ideas about what kind of plane to build. Mikoyan wanted to make a smaller, less expensive jet. Their E-721 would weigh between 16 and 17 tons, which is about 35,000 to 37,000 pounds. It would use two Klimov VK-10M engines, each producing between 10 and 11 tons of thrust. Sukhoi went the opposite way. Their T-50 would be bigger and more powerful, weighing between 22 and 23 tons. They planned to use two Lyulka Saturn AL-41F1 engines, each producing about 14.5 tons of thrust. In April 2002, Russia's Ministry of Defense picked Sukhoi over Mikoyan to lead the new fighter jet project. This wasn't just because of their good design. Sukhoi had proven themselves in the 1990s by successfully making different versions of their Su-27 jet and selling them to other countries. This success meant they had enough money to handle such a big project. The head of the Russian Air Force, Vladimir Mikhailov, said they planned to start test flights in 2007. Meanwhile, Mikoyan didn't give up. They kept working on their own smaller jet, the E-721, which they called the LMFS, meaning Light Multifunctional Frontline Aircraft in Russian, but had to pay for it themselves. When designing the Su-57, Sukhoi looked closely at America's F-22 stealth fighter. They liked some things about it, but wanted to fix what they saw as problems. The F-22 couldn't use its moving engine nozzles to help it roll side to side or turn left and right. It also didn't have much room between its engines to store weapons. And if its engine controls stopped working during extreme maneuvers, it would be hard to recover. Sukhoi didn't think the F-22 could carry enough weapons, especially since it mostly focused on air-to-air missiles. They needed their new jet to do more than that, and they designed it to fix all the problems they had envisioned. The Su-57 has a wide, smooth body that blends into its wings. Two engines sit far apart from each other. Both the tail fins and horizontal stabilizers at the back can move fully, and the tail fins angle outward to help hide from radar. The wings are shaped like triangles and have different moving parts along their edges to help control the plane. The engine's nozzles can point in different directions, giving the pilot more control. The plane has special extensions where the wings meet the body. These push the plane's balance point forward, making it less stable but more agile. These extensions have moving parts that help control airflow and keep the plane steady, even if the engine controls stop working. To slow down in the air, the plane's wing parts move up and down, while the tail fins turn inward to catch more air. While most of the plane is made from metal, it also uses a lot of composite materials. These make up about 22 to 26% of the plane's structure and cover about 70% of its outer skin. The designers had big plans for the Su-57 from the start. They wanted it to carry lots of weapons inside the plane instead of hanging them underneath. Between its two engines, there's a large space with two main weapon bays, one behind the other. There are also smaller bays near where the wings join the body with special triangle-shaped covers. Keeping weapons inside helps the plane in two ways. It stays stealthy because nothing is sticking out to see on the radar, and it can fly better because nothing is creating extra drag. The Su-57 can move with incredible control in any direction, thanks to three main features: its naturally unstable design, which helps with control, its advanced KSU-50 flight control computer, and its angled engine nozzles that can point the thrust. These features let pilots safely perform extreme maneuvers, like the Pugachev's Cobra, where the nose points straight up while flying forward, or the Bell maneuver where the plane seems to hang in the air. The plane can even rotate in place without losing much height. The way it's built, along with its powerful engines, lets it reach twice the speed of sound. It can even fly faster than sound without using its afterburners, cruising at 1.3 times the speed of sound. This gives it a big advantage. Its weapons can reach farther than older fighters' weapons could. With its large fuel tanks, the Su-57 can fly at supersonic speeds for more than 930 miles, which is over twice as far as the older Su-27 could go. If pilots need to fly even farther, they can extend a probe to refuel in the air. The Su-57 is the first Russian military plane built to hide from radar. Think of it like hiding from a flashlight beam. The plane uses several tricks to avoid being seen. Just like the F-22, its edges are lined up in a way that makes radar bounce away instead of back to the source. The edges of the wings and control surfaces are set at careful angles, and even the skin panels have jagged edges, all to scatter radar signals in different directions. Instead of hanging weapons on the outside where radar can spot them, the plane keeps them tucked away inside. The antennas sit below the surface of the skin rather than sticking out. The plane's surface is also covered with special materials that soak up radar waves like a sponge, making it harder for radar to get a clear picture of the aircraft. When the plane's heat-seeking sensor isn't being used, it faces backward, and its backside is coated with radar-absorbing material. The engines could show up clearly on radar, like a bright spot, so the designers had to get creative. They lined the air intake tunnels with special radar-absorbing coating and made them curve like a snake. This helps hide the front parts of the engines. For the parts people can still see, they put a slanted metal grid in front, placed about 0.7 to 1.2 times the width of the tunnel away from the engine. It's the same trick used on the Boeing FA-18EF to make the engines harder to spot on radar. The whole plane is built with much tighter measurements than older Russian fighters. Think of it like building with Lego blocks. The pieces need to fit together perfectly with no gaps to keep the plane hidden from radar. By combining its special shape and radar-absorbing coating, the Su-57 is 30 times harder to spot on radar than the older Su-27. The Su-57 uses two special engines called AL-41F1s. Think of them as super-powered versions of older Russian jet engines. When running normally, each engine can push with a force of 9 tons. These engines have a smart computer brain that controls them automatically. It's connected to the plane's flight controls, which helps the pilot steer and handle the aircraft more easily. The engines also have some clever features to help them work better. When the plane flies very fast, Special ramps in the air intake adjust to help the engines breathe better. There are also metal screens that can slide into place to stop rocks or debris from getting sucked into the engines. This is helpful when the plane needs to take off from rough airfields. But these engines have had some problems. Back in 2011, at an air show in Moscow, one of the planes had to stop taking off because its engines started having trouble. Later in 2014, the Indian Air Force said they were worried about how well these engines worked and how reliable they were. Russia is developing an improved Su-57 fighter jet. In the mid-20s, they plan to equip it with new AL-51F1 engines. These engines will be much more powerful, with 11 tons of thrust normally and 17 tons with afterburners. They'll also be more reliable, efficient, and cost less to maintain. To avoid detection, the engines will have a lower radar cross-section and give off less heat. Special materials in the front section and jagged exhaust nozzles help reduce their radar signature even further. So in a few years, the Su-57 should be stealthier, more powerful, and more dependable thanks to its cutting-edge engines. A big step up for Russia's most advanced fighter. In 2023, the engine makers started working on something different, a flat exhaust nozzle instead of the usual round one. They started testing it in late 2024. Since they had to make this new nozzle fit the existing plane, they designed it carefully so they wouldn't have to make big changes to the rest of the aircraft. Inside the Su-57's body, there are 4 hidden spaces to carry weapons. The 2 main spaces run down the middle of the plane, each about 4.4 meters long and 0.9 meters wide. 2 smaller triangle-shaped spaces sit on the sides, tucked under where the wings meet the body. To launch these weapons, the plane uses special racks made by a company called Vimpel. The main compartments have 2 kinds. One type can handle weapons up to 300 kilograms, while the stronger type can handle heavier weapons up to 700 kilograms. The side compartments use a different kind of rack to hold their weapons. The plane has room for 6 missiles to shoot down other aircraft. 4 bigger ones fit in the main weapon bays in the middle of the plane, while 2 smaller ones tuck into the side bays. For fighting other planes at medium distances, it uses the KR-77M missile. This is a better version of an older missile, with new features like a smarter radar seeker in the front and an improved motor that fires twice. For close-up fights, it uses the R-74M2 missile, which follows the heat from other aircraft. They made this missile skinnier so it could fit inside the plane's weapon bays. They are also working on a completely new short-range missile called the KMD to replace it someday. When the plane needs to hit targets far away, it can use an even bigger missile called the Izdelie 810. This is an upgraded version of another missile, made shorter so it fits better inside the plane. The plane can carry 2 of these in each main weapons bay. If needed, it can also hang the older version of this missile on the outside of the plane. The pilot looks at 2 big screens that are 38 centimeters across and about the size of a laptop screen. These screens show all the important information, just like in the Su-35S. There's also a smaller screen and a control panel with buttons. Instead of old-style dials and gauges, everything is digital. Up at eye level, there is a display that projects flight information onto a clear screen, so the pilot doesn't have to look down. It shows a view that's 30 degrees wide and 22 degrees tall. To fly the plane, the pilot uses a joystick and 2 throttle levers. All the main controls are right there on these 2 handles. The pilot can control most things without moving their hands away. The clear cover over the cockpit comes in 2 pieces. The back piece slides forward to close up. This cover has a special metal coating on it to help hide the plane from radar. The plane uses a Russian-made computer system to run everything, based on a chip called the 1890 VM8YA. One of the key goals for the Su-57 is to get all its electronics working together seamlessly. The fancy term for this is sensor fusion. When everything talks to each other, it makes the pilot's job a whole lot easier. They can see the full picture without having to juggle a bunch of different info. The plane's computer brain is called the Information Management System. It's the thing that keeps all the other systems in sync. The 2 big ones are the Sh-121 radio system and the 101KS atoll cameras and sensors. Sukhoi is handling the electronics integration in-house, which is a big job. The software has over 4 million lines of code. They're using fiber optic cables to keep everything connected. Russia's defense ministry shared some big news on Christmas Day 2020. They said the Su-57 had officially joined the Air Force. The first production planes were sent to a base in Lipetsk, in the southern military district. These initial jets will be used to figure out tactics, train crews, and put the Su-57 through its paces. They want to see how it performs day to day. The first unit set to fly the Su-57 full-time is the 23rd Guards Fighter Aviation Regiment. They are based out east, right next door to the factory. In May 2022, a couple of months into Russia's invasion of Ukraine, some Russian sources said they had sent Su-57s into the fight. The claim was that these stealth jets fired missiles at Ukrainian targets from long range, keeping well clear of Ukraine's air defenses. Then in June, the RIA Novosti news agency reported that 4 Su-57s had teamed up over Ukraine to hunt down and wipe out Ukrainian air defense systems. The Russians said this network of stealth fighters showed off the Su-57's radar-dodging tricks in a real combat situation. So if these reports are accurate, Russia's cutting-edge Su-57s have gotten a taste of combat in Ukraine. But just like the rest of the Russian Air Force, they're having to play it safe and keep their distance to avoid Ukraine's surprisingly tough air defenses. The Su-57 fighter jet is packed with cutting-edge tech that will make pilots' lives easier and help it sneak past enemy radars. The Russians are betting big on this plane, hoping it will give their Air Force a serious boost in the coming years. On May 8, 2026, the U.S. government released classified UFO files that confirm what researchers have been saying for decades. Not grainy footage, not pilot testimonies that get dismissed at press briefings. Actual program documents from inside the U.S. intelligence apparatus confirming that non-human craft have been recovered. But here's what the headlines are missing. The real story isn't that UFOs are real. It's that the U.S. has had them for decades, handed them to defense contractors, and has been quietly learning how to fly them. The release covers documents spanning multiple agencies, including the Defense Intelligence Agency, the Office of Naval Intelligence, and several programs that had no public name until this month. What makes this different from every prior disclosure is the language. Previous releases talked about unidentified aerial phenomena in careful, detached terms. These documents use phrases like recovered non-human origin craft and material of non-terrestrial manufacture. That's not bureaucratic hedging. That's an admission. The scope of what dropped in May is wide, but it's the gaps that tell the deeper story. Whole sections are redacted. Specific program names appear once and then disappear behind black bars for the next 30 pages. You can see the shape of something much larger being deliberately kept out of frame. Several documents reference programs that connect directly to known black budget operations. The names won't be familiar to most people, but defense researchers have been tracking anomalous budget line items for years. Money that flows into programs with no public description and no congressional oversight record. What the May 8th files do is start filling in what some of that money was actually for. So why release any of this now? The answer is congressional pressure that's been building since 2023, combined with whistleblower protection legislation that made it legally safer for insiders to come forward. The UAP Disclosure Act forced the hand of agencies that would have sat on this indefinitely. Multiple former program officials had already testified under oath to the Senate Armed Services Committee that recovery programs existed. Once that's on the congressional record, full suppression becomes harder to maintain. Then there's AARO, the All-Domain Anomaly Resolution Office, which was set up in 2022 and spent 2 years publicly stating there was no evidence of recovered craft or reverse engineering programs. The May 8th documents directly contradict that position. Reports from inside AARO's own analysis chain reference material studies and propulsion research that don't match anything in the known aerospace inventory. The office was telling Congress one thing while its own classified reporting said something else entirely. One document that's getting a lot of attention references a program structure described as a tiered controlled access program, meaning it's classified above top secret in a way that legally exempts it from standard congressional oversight. That structure is how you hide something for 50 years without a single budget hearing exposing it. The program isn't in the black budget because it technically doesn't exist inside the normal classification architecture. It exists in a separate layer that most of the government can't even ask about. What's confirmed in the files, taken together, is this. Craft of non-human origin were recovered. Materials from those craft were transferred to contractors for analysis, and at least some of that work involved propulsion systems that don't match any known physics framework. The documents don't explain how far that work progressed, but they confirm it happened, and they confirm it's been happening for a long time. The files confirm recovery. But recovery is only the beginning of this story. What the US did with what it found, who did the work, and what they've actually built from it, that's what the next layer of documents starts to reveal. If you wanted to hide the most advanced aerospace program in human history, Lockheed's Skunk Works facility in Palmdale, California, is exactly where you'd put it. This is the same operation that built the U-2 spy plane in total secrecy during the 1950s, then followed it with the SR-71 Blackbird, which flew so fast and so high that nothing could touch it. Then came the F-117, the world's first operational stealth aircraft, which the Air Force publicly denied existed for years while it was already flying combat missions. Skunk Works doesn't just build classified aircraft. It builds things the rest of the world won't believe are possible until they're already obsolete. The May 8th files reference contractor involvement in material analysis going back decades. Lockheed is named in connection with propulsion research tied to recovered craft, and the language used isn't vague. One document describes a materials transfer to a cleared defense contractor facility for analysis of non-conventional propulsion elements. Skunk Works has the clearance infrastructure, the physical security, and the engineering depth to run exactly that kind of program without a single public trace. Raytheon's role is different, but just as telling. Where Lockheed is about airframes and propulsion, Raytheon specializes in the sensor and weapon systems that would need to interface with whatever gets built. Their classified divisions have been working on directed energy weapons and advanced electromagnetic systems for years, and several of those programs have budget lines that dwarf their known output. If you're reverse engineering a craft that manipulates electromagnetic fields for propulsion, you need Raytheon-level expertise to understand what you're actually measuring. Their involvement points to a program that's moved well past basic materials analysis into something that requires operational hardware. The structure that makes all of this legally possible is called a Controlled Access Program, or CAP. It sits above top secret clearance and operates outside the standard congressional budget review process. A program inside a CAP doesn't appear in defense appropriations hearings. It doesn't get reviewed by the Armed Services Committee. The people running it can legally tell senators it doesn't exist, because inside the classification framework, it technically doesn't. This is how you spend decades and billions of dollars on something with no public record. The money moves through layers of contractor sub-accounting that were specifically designed to be untraceable. Bob Lazar described this exact architecture in 1989. He said he worked at a facility near Area 51 called S4, where 9 recovered craft were stored and studied. He described a propulsion system built around a stable isotope of element 115, which he called moscovium, that generated a gravitational field used for propulsion. At the time, element 115 didn't officially exist on the periodic table. It was synthesized and confirmed in 2003. Lazar's technical descriptions were specific enough and accurate enough on points that couldn't have been guessed that dismissing him as a fraud requires ignoring a lot of inconvenient detail. The May 8th files don't mention him by name, but the propulsion research they reference lines up with what he described 37 years ago. Where does the money come from? Defense analysts who track black budget allocations have flagged a category of aerospace spending that's grown by roughly 300% since the early 2000s, with no corresponding increase in known program output, no new aircraft, no announced propulsion contracts, no patents filed. That money went somewhere, and based on what the files released describe, the answer is becoming harder to argue with. Start with what Navy pilots actually recorded, because that's where the physics breaks down in a way you can't explain away. The Tic Tac incident from 2004 gave us something rare: military sensor data, trained observers, and a craft that performed maneuvers no known aircraft can execute. Commander David Fravor watched it drop from 80,000 feet to sea level in under a second, stop dead, then accelerate in a completely different direction with no transition, no arc, no deceleration curve. Just an instantaneous change of vector at speeds that would reduce a human pilot to a stain on the seat. The G-force involved in that kind of movement, by any conventional physics calculation, would be somewhere between 400 and 700 Gs. A human body starts losing consciousness around 9 Gs. Whatever was inside that craft, if anything was, it wasn't being subjected to the same forces the airframe was generating. That's the first thing that separates these craft from everything else. They don't appear to be affected by inertia. When your car accelerates, you feel it push you back into the seat because your body has mass and resists the change in motion. These craft move as if that relationship between mass and acceleration has been switched off. The engineering community's best working theory is electromagnetic field manipulation, where the craft generates a localized field that essentially warps the space it's moving through, so the craft and everything inside it moves together without experiencing the directional forces that would normally apply. You're not pushing through space, you're moving the space around you. Then there's the propulsion signature, or more accurately, the complete absence of one. Every aircraft ever built leaves traces. Heat bloom from engines, exhaust gases, a pressure wave that generates a sonic boom above the speed of sound. These craft produce none of that. Radar tracks them at speeds well above Mach 1 with no sonic signature. Infrared sensors find no heat output. There's no jet wash, no plasma trail, nothing that conventional propulsion would leave behind. Whatever is moving them isn't burning anything and isn't pushing against the air. The altitude performance compounds this, from a standing hover at low altitude to above 80,000 feet in a matter of seconds, with no acceleration phase, no engine spool up, no detectable thrust vector. That's not improved propulsion, that's a different category of physics entirely. Stealth properties add another layer. These craft don't just absorb radar the way an F-22 does with its angled surfaces and radar-absorbing materials. They disappear from multiple sensor types simultaneously. Radar, infrared, optical tracking, all go blank at the same moment. That kind of cross-spectrum disappearance suggests the craft can manipulate its own electromagnetic signature across every detection wavelength at once, not just deflect one type of sensor. Now factor in the TR-3B, a triangular craft reported independently by dozens of witnesses across multiple countries over the past 30 years, always described the same way. Silent, slow-moving at low altitude, capable of accelerating away at speeds that leave no trace on radar. The consistency of those descriptions across unconnected sources is hard to write off. If the reverse engineering programs described in the May 8th files produced a flying prototype, a triangular platform would be a logical airframe choice for a craft using field-based propulsion rather than conventional thrust. Even replicating 20% of what these craft can do would make the result invisible to every air defense system on the planet. No radar lock, no heat-seeking missile track, no intercept solution. If the US has crossed that threshold, the gap between American air power and every other nation isn't measured in generations. It's measured in physics. China's DFZF hypersonic glide vehicle tops out around Mach 10. Russia's Avangard system reaches Mach 27 under ideal conditions. Both represent years of development and genuine engineering achievement. They're also still moving through the atmosphere the same way a rock moves when you throw it, subject to drag, heat, gravity, and tracking solutions that improve every year. Western air defense systems have already started adapting to hypersonic threats. The physics is understood. The countermeasures are being built. A craft that produces no radar return, no heat signature, and no inertial profile isn't a faster version of the same problem. It's a problem that existing defense architecture has no answer for, because every detection and intercept system ever built assumes the target is operating inside Newtonian physics. You can't compute an intercept solution for something that changes direction instantaneously. You can't guide a missile to a heat source that doesn't exist. You can't jam a craft that's already invisible to every wavelength you're transmitting. That's what makes the strategic gap here different from any prior technology advantage. When the US fielded the F-117, it took years before adversaries developed radar systems capable of tracking low observable aircraft. Eventually, they did. The physics was still the same, just harder to work with. What the May 8th files point toward is a capability that doesn't give adversaries a longer timeline to adapt. It gives them no pathway at all, because the underlying physics isn't an evolution of what they already understand. The surveillance applications alone would reshape geopolitics entirely. A platform that can reach any point on Earth undetected, loiter without any thermal or electromagnetic trace, and exit before any response is mounted gives the US an intelligence collection capability with no precedent. Every facility, every command structure, every weapons program a foreign government believes is hidden becomes visible, and they'd never know it happened. That's why this stayed buried for so long. Releasing it doesn't just trigger an arms race. It collapses the entire framework of mutual deterrence that international security has been built on since the 1950s. Every treaty negotiated under the assumption that both sides had roughly comparable detection and strike capabilities becomes meaningless. Every military alliance recalculates its value. The geopolitical order restructures overnight and not in ways anyone can fully predict. Lockheed and Raytheon aren't going to confirm any of this. The program managers who ran these operations signed agreements that don't expire and carry criminal consequences. But the May 8th documents are doing something those individuals can't stop. They're assembling the outline of a program that was never supposed to have an outline. Each redacted page still shows you where the edges are. And the edges are a lot larger than anyone outside this program was supposed to know. The US didn't just recover something. It spent decades turning that recovery into operational hardware, and the rest of the world is only now finding out that race was run without them. What dropped isn't the end of the story. It's the first time the story got official edges. The US has been flying ahead of the known world for decades, and the files are finally saying what the contractors never will. Somewhere inside a classified hangar, there may already be an aircraft that can reach any city on Earth in under 90 minutes, drop a strike from the edge of space, and land back on a runway before the enemy even confirms what hit them. No government has officially acknowledged it. No journalist has photographed it. And yet China and Iran are restructuring their entire air defense doctrine around the possibility that it's real. That's not speculation dressed up as news. That's the logical conclusion of a pattern that skunkworks has been running for decades, and it's a pattern worth paying close attention to. What we're talking about is a program that circulated in defense analyst circles under the name Phantom Wing, a black project allegedly developed inside Lockheed's most secretive division, built to operate at the boundary where atmosphere ends and orbit begins, and designed to strike from a domain that no adversary currently has any answer for. By the end of this video, you'll understand exactly why this aircraft, if it exists, doesn't just change the speed of warfare, it changes the entire math adversaries use when they think about confronting the United States. We're going to cover where this program allegedly came from, how orbital strike actually works, why neither China nor Iran can stop it, and what's real versus what's still in the rumor layer. Let's get into it. The SR-71 Blackbird was officially retired in 1998. For 25 years, it held the record as the fastest air-breathing aircraft ever flown, capable of outrunning surface-to-air missiles simply by accelerating away from them. When the Air Force stood those airframes down, the public story was that satellites had made high-speed reconnaissance redundant. Cheaper, safer, no pilot at risk. Lockheed accepted that narrative publicly and kept working privately. That's not a conspiracy framing. That's just what skunkworks does. The division was built by Kelly Johnson in the 1940s specifically to work outside normal bureaucratic visibility, and every major platform it's produced followed the same arc. Something gets developed in secret, flies operationally for years, and only surfaces publicly when the program has moved far enough along that disclosure, no longer compromises it. The F-117 Nighthawk is the cleanest example. It flew its first operational mission years before the Pentagon acknowledged the aircraft existed. Neighbors near Tonopah Test Range in Nevada were seeing a delta-shaped aircraft in the sky throughout the early 1980s. The official confirmation didn't come until 1988. By that point, the aircraft had already been combat-ready for years. The B-2 Spirit followed the same pattern. The SR-72 followed it too, except in that case, Lockheed themselves broke the silence. In 2013, they published a concept article in Aviation Week describing a hypersonic successor to the Blackbird, targeting Mach 6, built around a combined cycle engine that could handle both subsonic and scramjet regime flight. The reason they disclosed it wasn't because the program was new. It was because the underlying propulsion technology had matured enough that keeping it completely dark was no longer the point. What matters about the SR-72 disclosure is what it implies. Lockheed went public with a Mach 6 reconnaissance and strike aircraft in 2013, which means the development timeline for that system stretches back well before that. And since 2013, Skunk Works has gone almost completely quiet on where that program stands today. That silence is meaningful. The phantom wing concept, as it's circulated among defense analysts and in patent filings tied to advanced propulsion and thermal protection systems, isn't described as a faster version of the SR-72. It's described as a categorically different kind of aircraft, not a hypersonic jet that flies through the upper atmosphere at high speed. Something that climbs above the atmosphere entirely, uses low orbital mechanics to cover distance, and then descends on a target from above at hypersonic velocity during re-entry. That's a different machine. It operates in a different domain, and the defenses that exist to stop conventional aircraft, or even conventional hypersonic missiles, weren't built with this flight profile in mind. To understand why that matters so much, you need to understand what orbital strike actually means mechanically, and why the physics of it are so difficult to defend against. Think about a standard strike mission. An aircraft takes off, flies through the atmosphere at some altitude, crosses into hostile airspace, releases a weapon, and exits. The entire flight path stays inside the same layer of air that weather systems move through. That's the domain every air defense network on Earth is designed to cover. Orbital strike works on completely different geometry. The aircraft climbs steeply after takeoff, burns through the upper atmosphere, and crosses into the region where air is too thin to generate conventional lift. At that altitude, the curvature of the Earth itself becomes the flight path. The aircraft isn't flying over the planet so much as it's arcing around it, using near-orbital mechanics to cover thousands of miles in a fraction of the time any conventional aircraft could manage. Then it pitches down, bleeds velocity through re-entry, and descends on the target from almost directly above. That descent profile is where the 90-minute global reach number comes from. At hypersonic re-entry speeds, the distance between a launch point in the continental United States and a target on the other side of the world stops being measured in hours. It's measured in the time it takes to arc through low orbit and come back down. The physics behind this aren't theoretical. China's DFZF hypersonic glide vehicle uses a related principle. Boost a warhead to extreme altitude and velocity, then let it glide and maneuver during descent rather than following a ballistic arc. The phantom wing concept, as described by analysts tracking the program, takes that same logic and applies it to a reusable crewed or semi-crewed platform. Not a missile you fire once. A vehicle that returns to base, gets serviced, and flies again. Getting there requires solving one of the hardest problems in aerospace engineering: transitioning an aircraft from conventional turbine flight at low speed through the transonic and supersonic regimes all the way to Mach 6 and beyond demands an engine that can function across that entire range without stalling, melting, or losing thrust at the worst possible moment. Scramjet engines only ignite efficiently above roughly Mach 4, which means the propulsion system has to bridge that gap. A combined cycle engine starts as a turbine, accelerates the aircraft to the speed where scramjet combustion becomes viable, then transitions cleanly to hypersonic mode. Lockheed's work on this problem goes back years, and the SR-72 program was built around making that transition reliable enough to be operational rather than experimental. Once the aircraft is above the atmosphere and descending, something interesting happens with stealth. At the speeds involved during re-entry, friction with the upper atmosphere generates a plasma sheath around the airframe. That layer of ionized gas absorbs radar energy rather than reflecting it back to a ground station. Conventional stealth coatings work by shaping the aircraft to scatter radar returns. The plasma effect works by swallowing the signal entirely. The aircraft is, in practical terms, invisible to ground-based radar during the exact phase of flight when it's most dangerous. The X-37B program adds another layer to this. The Air Force's unmanned spaceplane has been flying classified orbital missions for years, with individual sorties lasting many months. The official explanation covers technology demonstration in a general sense, but several defense analysts have noted that the vehicle's flight profile, its re-entry characteristics, and the thermal protection systems it uses are all directly applicable to a crewed or strike-capable successor. Whether the X-37B is a direct ancestor of something like the Phantom Wing, or simply a parallel program solving overlapping problems, the technology it's validating maps cleanly onto what an orbital strike aircraft would need to survive and function. That gets at why China and Iran aren't just watching this program with curiosity. They're watching it with urgency, because the defense gap it creates isn't something either country currently has any real answer to. China's most capable ground-based air defense network is built around systems like the HQ-9 and its naval equivalents. These are serious, modern platforms. They can engage targets at long range, they're mobile, and they're designed to handle multiple threats simultaneously. Against a conventional strike package, they'd cause real problems. The word conventional is doing a lot of work in that sentence. Every air defense system ever fielded is fundamentally a solution to a geometry problem. A radar acquisition system scans a defined volume of airspace, detects a target moving through it, hands off tracking data to a fire control system, and that system calculates an intercept trajectory and launches. The whole chain depends on one assumption, that the threat is coming from a direction and altitude the radar was designed to watch, with enough time in the engagement envelope to actually intercept it. An orbital strike aircraft breaks every variable in that chain at once. The descent profile we covered earlier means the threat arrives from almost directly overhead, not from the horizon where most radar apertures are optimized to look. The angle alone creates a detection problem that no software patch fixes, because it's baked into the physical orientation of the antenna arrays. To cover orbital re-entry angles, you'd need a fundamentally different sensor architecture pointed at the sky rather than the horizon, networked with fire control systems fast enough to generate an intercept solution in an extremely compressed window. That window is roughly 90 seconds or less from initial detection to impact, assuming the radar can acquire the target at all through the plasma sheath effect. 90 seconds is not enough time for any currently fielded intercept system to run a full engagement sequence against a maneuvering hypersonic vehicle descending from near orbital altitude. The missile has to be in the air before the geometry becomes workable, and you can't do that if you don't know the target is coming. Iran's situation is considerably more exposed. Their air defense inventory leans heavily on Russian origin systems, some of which date back decades. These aren't platforms designed to engage targets moving at hypersonic speeds under any geometry, let alone the near-vertical descent profile orbital strike produces. During the strikes attributed to Israel in recent years, Iranian systems struggled to consistently engage much slower, much lower-flying threats. The gap between what they operate and what an orbital strike aircraft represents isn't a gap you close with training or tactics. There's a psychological layer here too, and it matters as much as the technical one. Conventional deterrence works because both sides can see each other's capabilities developing in real time. Satellites track airfield construction, analysts count aircraft tail numbers, intelligence services monitor production rates. That visibility allows adversaries to calibrate their posture. They can assess the threat, build a response, and communicate that response as a deterrent of their own. An aircraft that can loiter in orbit for extended periods and descend without warning removes that visibility entirely. There's no ingress track to detect, no tanker support to monitor, no pre-flight activity to tip off intelligence collection. The first indication that a strike is happening could be the strike itself. Ballistic missiles follow a predictable arc from launch to impact, and that predictability is actually one of their weaknesses from a deterrent standpoint. Terminal defense systems have known intercept geometries to work with. A vehicle that maneuvers during descent on a profile that originates above the atmosphere doesn't give interceptors a predictable arc to solve for. That's not a marginal improvement in survivability. That's operating in a domain where the intercept math doesn't currently exist. So let's be straight about where the line sits between confirmed and alleged, because they're not the same thing, and collapsing them doesn't serve anyone. What's confirmed, the SR-72 program is real, Lockheed said so publicly. Skunk Works operates on black budget funding that's documented in congressional appropriations history. The X-37B is flying right now, somewhere above your head on a mission the Air Force hasn't fully explained. The physics of orbital re-entry and plasma stealth aren't classified. They're published aerospace science. Those things are facts. The Phantom Wing name isn't. The specific capability claims aren't. What circulates in defense analyst communities is a composite assembled from patent filings on advanced thermal protection and combined cycle propulsion, from signals intelligence reporting that's never been officially sourced, and from the kind of inference that happens when people who track black programs for a living notice line items in the Pentagon's budget that don't match anything on the acknowledged aircraft list. That's not nothing. It's also not a confirmed program. Here's why the Pentagon might not mind that ambiguity existing. An adversary that believes this aircraft is already operational has to plan for it. They have to spend money on detection architecture they don't currently have. They have to redesign missile defense doctrine around a threat profile their engineers are still trying to model. They have to absorb the psychological weight of knowing there may be a weapon in their opponent's inventory they have no answer for. All of that happens whether or not the platform has actually completed its first operational flight. Strategic ambiguity isn't a side effect of secrecy. Sometimes it's the product. The budget signal points in one direction. Unacknowledged special access programs have consumed a growing share of U.S. defense spending over the past decade, and the gap between total black budget allocation and the programs analysts can account for by name has widened. Something is absorbing that money. Multiple somethings, probably, and the historical pattern keeps repeating. The F-117 was a rumor, then a fact. The B-2 was a rumor, then a fact. The SR-72 itself was analyst speculation until Lockheed published it. Every one of those programs followed the same arc: denial, silence, then confirmation after the technology was mature enough that disclosure cost nothing strategically. Nobody outside the program knew the truth until Skunk Works decided they could afford to share it. That's exactly where the Phantom Wing sits right now. Either it's already flying and we're in the silence phase, or it's close enough that the rumors are doing useful work in the meantime. Both possibilities produce the same outcome for China and Iran. Whether the Phantom Wing is airborne tonight or still years from its first flight, the gap it represents is already reshaping how adversaries think and spend. China and Iran aren't building next-generation air defenses because they feel secure. Subscribe for more and check out the next video on screen.